So this is about the transistor based RC phase shift oscillator. Okay, we have RC circuit in the feedback side, and R dash is for is a kind of an input resistance. Okay, so we don't want to think much about the design right now. Okay, I'm moving on to the next one, the op amp. In the op amp circuit, why I have included this circuit in the presentation is because in the Wien bridge oscillator we have used the op amp only. I hope I will circulate the materials very soon. Okay, in the Wien bridge oscillator, if you see, we have given the input to the positive terminal. Okay, input in the positive terminal, because in the Wien bridge oscillator the feedback network will not provide any phase shift. The phase shift provided by the feedback network is 0 degree. So I am taking the input to the positive terminal so that the feedback provided by the amplifier will also be 0 degree. So overall feedback is 0 degree. Okay, that is for the Wien bridge oscillator. Here we are having a RC phase shift oscillator. Since this feedback network here, this feedback network guy here, the feedback network guy here actually actually give a phase shift of 180 degree. So we want another 180 degree to make it as a 0 degree phase shift. So here a 180 degree, the feedback network will provide a phase shift of 180 degree, and this op amp here will provide a phase shift of 180 degree, because that's why you are giving your input to the inverting terminal. When you are inverting an input, it will give automatically, it will give a phase shift of 180 degree. So 180 plus 180 degree, it will give overall a 360 degree. That's why we just want to make a comparison between the Wien bridge oscillator and RC phase shift oscillator. Okay, anyway, both have only the resistor and the capacitor components in their feedback network. Okay, all you have to understand is this RC phase shift oscillator, the feedback network will provide a phase shift of 180 degree, and the Wien bridge oscillator, the feedback network will provide a phase shift of only 0 degree. It won't provide any phase shift at all. Okay, so we don't worry much about the phase shift there. Fine, I'll move on to the next one, because here there are some RC combinations, and we want to know what is happening within the RC combinations, right? So I am taking right now we will take only one RC network for analysis. I am taking just one RC network for analysis. Okay, just one RC network. Here, if you see, the input is given to the capacitor, and the output is the input is given to the capacitor. That means the output of the op amp is given to the input to the capacitor, and the output is taken across the resistor. Okay, whoever is unmute, please mute yourself. Okay, so I'll move on to the next one. I just take only one RC network, and we will analyze what happens with that network. Okay, so here we have the input voltage V in and the output voltage V out. So if I am writing the transfer function, that means if I am taking the output voltage, I am taking the output voltage across the resistor. So the output voltage will be equal to the resistor value R divided by the total resistance. That means the total impedance R minus, here you can see, here you can clearly see that the resistance that is being taken across R, consider V in is here. V in is multiplied here, and it is not here. Okay, so V out is equal to the resistance R divided by the total resistance, that is resistance R plus the impedance of the capacitor. Okay, Xc is nothing but your reactive capacitance. Okay, so in this way I can write what is the value of the output impedance. So with the value of the output impedance, we can write the gain. That means just by taking this V in the denominator of the left side. So I'm just erasing all that ink. Okay, so here we can see Xc is inversely proportional to the frequency of the operation. Omega is the angular frequency. Okay, now we will be calculating the angle. What is the angle that is being calculated for one RC network? Okay, only one RC network we are having here. In the numerator, if you see the numerator of this, there is no imaginary part, correct? So here j r plus j into 0. Okay, imaginary part is actually 0. So when I'm taking an angle of a complex number, it will be tan inverse of the value that is in the imaginary part, tan inverse of b by a. Hope you remember that b is the imaginary part number and a is the real part number. Okay, so here the imaginary part number is 0, so my angle will automatically be 0. Okay, minus the angle in the denominator here. The angle in the denominator is given by tan inverse of minus xc, because the imaginary part value is minus xc here, minus xc here. So I am writing minus xc divided by the real part value. This is given on a whole. We will be getting the face value 0 degree minus tan inverse of minus xc divided by r. Okay, we know that minus tan inverse of minus some value will be tan inverse of that value, because tan inverse of minus theta is minus tan inverse of theta. So this will be changed to tan inverse of xc divided by r. Okay, this is very important. Okay, just let me know if you don't understand it here. Yeah, please mute yourself, whoever it is. Making this xc as 0, then the phase shift will go to 0 degree. When I am making the resistor 0, then the phase shift is going to 90 degree. So effectively, one RC circuit can provide a phase shift of 90 degree. Okay, so theoretically, if you 0 thing. Okay, so what we are doing is we are accommodating one more RC network, because with the two RC circuit we can provide at the max you can provide 180 degree, but practically that is not possible. So anyway, it will be less than 180 degree, but I want a 180 degree phase shift there. Okay, so what we are doing is instead of two RC networks, we are going for three RC circuits. Okay, so each RC circuit will provide approximately a phase shift of 60 degree. So we will be getting a overall phase shift of 180 degree there. Okay, so at least that's why at least three stages of RC circuit is required in the feedback network. Fine. Okay. Now we will write the resonant frequency on derivation. See, this derivation is so long, so I just ignored. But in the previous Wien-Bridge oscillator, we have derived the value of the beta and the resonant frequency clearly. The same procedure is applied here. Okay, the thing is the derivation part of this resonant frequency is a little large, so I am not including it here. Okay, so when you see the resonant frequency, that will be equal to 1 by 2 pi RC. Here it is, 1 by 2 pi R into C into root of 2n, where n is the number of stages of RC. Okay, here our n number of stage of RC is 3. We are using 3 stages of RC networks, so it will be the resonant frequency FR will be 1 by 2 pi RC into root of 6. Okay, so that is for a 3-stage RC network, and the corresponding beta value that has been derived is 1 by 29. I hope you remember for the Wien-Bridge oscillator, the beta value is 1 by 3. Okay, here the beta value is 1 by 29. Okay, that is also one difference between this beta is nothing but the feedback ratio. So based on the requirement, we will be selecting whether we have to go for RC phase shift oscillator or a Wien-Bridge oscillator. Okay.
Two different
and
circuits.
Here, who is that? Priyadarshini, do you have a problem with your problem in muting? Okay. This is about the feedback RC network, and we just compare how this RC network and the Wien bridge oscillator, RC phase shift oscillator and the Wien bridge oscillator, what are all the common things and the difference. And this slide will actually highlight the main difference between the RC phase shift and the Wien bridge oscillator. Here you can see the first point, the RC phase shift oscillator is inversely proportional to 2 pi, the resonant frequency is given by 1 by 2 pi RC. We have additionally the term root of 2n here, wherein is the number of RC stages. Here it is very much direct. You just want to have what is the value of R and C here to find the resonant frequency. Okay, and for RC phase shift oscillator, the feedback ratio is 1 by 29. That means it will take very less amount of output and it will give us a feedback to the input. Whereas in the Wien bridge oscillator, it will take 1/3 of the output and it will give to the input. So the amplifier gain should be at least greater than 29, because A into beta should be nearly equal to 1, at least equal to 1, or it should be greater than 1 to start the oscillations. Okay, so we have A should be greater than or equal to, then only this loop gain A beta will be equal to 1 or greater than 1. Okay, so we have A should be greater than or equal to 29 here for the RC phase shift oscillator, which depends on the value of the beta. And here, if you see the value of the A should be greater than or equal to 3, because the value of the beta is 1 by 3 here. Then only A beta will be equal to, A beta will be greater than or equal to 1. Okay, that is the main condition for the oscillations. Okay, and here RC phase shift oscillator, as I said earlier, the feedback network will provide a 180-degree phase shift, whereas the Wien bridge oscillator will not provide any phase shift at all. Okay, that means 0-degree phase shift there. Since the RC phase shift oscillator provides a 180-degree phase shift, op-amp should be operated at the inverting mode. That means you should give the input in the inverting terminal. Whereas here, we don't have that problem, so we are giving the input in the non-inverting terminal. In non-inverting terminal means we are giving the input in the plus. Okay, fine. Okay, now also Wien bridge oscillator has this tuning. The tuning things is very easy, because we don't have to worry about the number of stages of RC there. We have only one stage of RC and we can easily tune it to whichever frequency is required. Okay, that is the main advantage of the Wien bridge oscillator. Fine. So this is about the RC oscillator. We have LC oscillator and crystal oscillator to be discussed now. Okay, the one thing is LC oscillator. Okay, so when I say LC, L means inductor and C is capacitor. Okay, so the circuit whichever is having this inductor and the capacitor, a very famous circuit is tank circuit. They call that a capacitor and the inductor that is connected in parallel as a tank circuit. Consider in the first diagram, just consider that your capacitor is fully charged and the inductor is attached in parallel with, connected in parallel with the capacitor. Okay, and now the switch is open. When I'm closing the switch, what happens is it will start, the capacitor charge will be start discharging from there. Okay, where it will discharge? It will discharge to the inductor. In the inductor, what happens is, as you know, the inductor won't allow the sudden change in the current inside, and according to the Lenz's law, an opposing EMF will be generated that will actually make the current to flow in the same direction that has been flowing there. Okay, see, there is a difference between using an inductor and a resistor there. Okay, in case if it is a resistor, it will dissipate the energy in form of heat, whereas the capacitor will store the energy in the form of electrostatic force, and the inductor will store the energy in the form of EMF. Okay, electromagnetic field. Okay, that will charge the capacitor in the opposite direction. As you can see in the next pic here, I'll take the laser pointer. Here you can see the last pic here. The capacitor in this pic, just take this third pic here. When this capacitor is discharged, the inductor will again charge this capacitor in this opposite direction. Previously, it was being charged in this direction, okay, before connecting to an inductor, but now the capacitor is charged in this direction. Okay, so what happens is, if you are taking a multimeter or some CRO and you are connecting it as a capacitor, then there will be a change in the polarity of the capacitor capacitor as the capacitor is charging and discharging, and the charging direction is different every time. So we will be resulting in a sine wave. Okay, and also here the problem with the circuit, tank circuit, is this charges won't last for too long, because somehow, because of the resistive part it is there in that circuit, the energy will be getting lost there. Okay, that's why the oscillations are dying out in this tank circuit. Okay, so our aim is to make the oscillations with the proper gain, with the proper amplitude, and with the proper frequency. So what we are doing is we are using this LC circuit, that means this tank circuit, with the amplifier circuit, so that the amplifier, what that guy will do is it will amplifies when it is required. Okay, and we are going to use this LC circuit in the feedback as a feedback network. Fine. Okay, now as we know that tank circuit, this is a very famous equation. You might have heard this before. The resonant frequency of a tank circuit is 1 by 2 pi L into C. Okay, square root of L into C. Fine. Okay, now getting into the tuned oscillator circuit, as I said, there will be amplifier to manage the dying out of the dying out of the signal, to handle the damped oscillations of the signal. So along with that, we have three different components: X1, X2, and X3. Okay, these combinations of X1, X2, and X3, we can go for different combinations. Either this X1 and X2 can be capacitor and X3 can be an inductor. X1 and X2 can be an inductor and X3 can be a capacitor. Okay, and either we can use LC here, LC combination in X1 and X2, and we can leave that X3 without connecting anything. Okay, that will be also a tuned input and tuned output oscillator. Okay, when I am using a capacitor in X1 and X2 and inductor in X3, then it will be a Colpitts oscillator. When I am using an inductor in X1, X2 in the place of X1 and X2, and in the place of X3 we are using a capacitor, means then it will be a Hartley oscillator. Okay, we will discuss about the Colpitts oscillator. Okay, so this is the Colpitts oscillator. If you clearly see this, this is nothing but your same RF amplifier that we have discussed before, we have done in the lab. Okay, precisely this circuit here is clearly a RC coupled amplifier. Okay, we are taking a part of a output in a we are taking a part of our output through the feedback network. This is a feedback network here. Okay, here you can see X1 and X2 are C1 and C2, that is a capacitances, and the X3 is an inductor here. Okay, that is overall, that will be a tank circuit, and it should be noticed here. Here this guy, the middle, from the middle, this is actually grounded. This point here is actually grounded. Okay, that's why we are having a connection like this. Okay, so what happens is we are taking the output, and a part of the output that has been the part of the voltage that has been dropped across the C2, the part of the output that is dropped across the C2 is feedback to the input. Okay, this is about the working of a Colpitts oscillator. See, whatever we say, we if we want oscillations at some particular frequency, we want to select the proper values of the capacitor and the inductor. That's why we have the resonant frequency here. This is for the Colpitts oscillator particularly. Okay, the resonant frequency is 1 by 2 by root of L into CEQ, where CEQ means the equivalent capacitance. We are assuming that the capacitance, while during the operation, this capacitance will be acting as if they are in the parallel combination. So CEQ is equal to C1 C2 divided by C1 plus C2. Okay, so this is about the Colpitts oscillator. Colpitts oscillator, you have a RC coupled amplifier. Remember, you have a RC coupled amplifier directly, and the part of output is taken through the tank circuit. Your tank circuit is a feedback network here. Okay, that feedback network is going to decide at which frequency the signal should oscillate. Okay, for that the resonant frequency is given in that equation. Okay, so you want to follow this clearly. Okay, this is for lab as well. Fine. Okay, we have the Hartley oscillator as well. So for now I'm ignoring that because it has almost a similar kind of operation there. Okay, So we will move on to the crystal oscillator. The next type of oscillator is crystal oscillator. Initially about the RC oscillator and the Colpitt's Hartley and all LC oscillator. For LC oscillator only we discussed about the tank circuit. Now moving on to the crystal oscillator. Okay. So why we are going for a crystal oscillator? That is the first question to be answered. Okay. So why we need a crystal oscillator? You know, in RC and LC combinations, RC and LC oscillators, the frequency of operation will be changing. Frequency of operation, and then phase noise will be there. Phase noise and all those. I'm not introducing more technical terms. I'm just taking that frequency. Yes, you are very familiar with the frequency. The frequency may change due to the following parameters. One is the change in the temperature. If the surrounding temperature changes, then your anyway your component will have an effect on the temperature, surrounding temperature, and also the temperature that is being resulting due to the flow of current there. Okay, change in the temperature will result in a change in the frequency and the change in the power supply voltage. As you know, we have some problem with the DC power supply. At times we end up with some problem. Okay, that also have some impact on the will have an impact on the frequency of the RC or the LC oscillator. Okay, and also the component values. Okay, the component values are not the same because as the day progresses, the charge carriers or whatever things we are consider a transistor, we are having the minority carriers, majority carriers, and all those things. As the time goes on, those component values, the VBE value will not be same as 0.7 volt. Okay, so there will be some error because of that operation, because of the component values as well. Okay, and crystal oscillators. So that's why we are in the need of the crystal oscillators. Okay, that's why we are going for a crystal oscillator, and it will have a high level of stability. High level of stability means if there is a signal that is being oscillating at some frequency 10 kilohertz, if I am checking at the point 1 millisecond, it will be still at that frequency, and if I am checking at 100 millisecond, the frequency will be the same. The frequency and the amplitude will be the same. So that is called the stable signal. Okay, that means the signal is oscillating at a stable frequency. That's why the level of stability of the crystal oscillator is very high, and the crystal oscillator will also possess a very high quality factor, and its operation range is also very high. And one thing I forgot to tell you is that RC oscillators are used for low frequency applications, and LC oscillators are used for high frequency applications. High frequency applications in the sense RF frequency. It will use to have the RF frequency. Particularly RF frequency is used in your AM and FM receiver. Okay, that is the simplest of examples. And this RC is a small signal in the very low frequency applications. Okay, and here we have the frequency of operations from 100 kilohertz to 100 megahertz. Okay, hundreds of megahertz, actually hundreds of kilohertz to hundreds of megahertz. Okay, crystal oscillator can generate such a frequency of oscillations. Okay, we will see in detail about the crystal oscillator. First, how this crystal oscillator works? That's a question we have to answer. See, I have a crystal. Crystal means some metal, some kind of silica, some metal, piezoelectric material, some material is there. Okay. Now we will discuss for discussing how the crystal oscillator works. We have to discuss about the inverse piezoelectric effect. Okay. What does that mean? Is I'm connecting a piezoelectric material. This is the piezoelectric material here. This material is actually known as the piezoelectric material. Piezoelectric material is nothing but the crystal. Okay, this piezoelectric material is connected here, and these are the electrode plates. These are all the electric plates, we can say, and it is connected across a AC source here. It is connected with the AC source here. So AC source means it will have some frequency. So whatever frequency we are giving the input source, this piezoelectric material will start vibrating at that frequency. Okay, so if I'm giving 50 hertz, then this piezoelectric material will vibrate at 50 times it will be vibrating within a second. Okay, that's the property of this piece, and that is inverse piezoelectric effect. Normally people will discuss about the piezoelectric effect and the inverse piezoelectric effect. Here we discuss about the inverse piezoelectric effect first, because we want to know what is actually happening with the crystal. Okay. So I'm giving a voltage and I'm giving a AC voltage. This AC voltage will be operating at some frequency. Because of that is applied across the crystal, this crystal will vibrate at that frequency. Okay, now what we are going to do is we are going to analyze what happens with the piezoelectric effect. In the piezoelectric effect, I'm just applying an external force in that crystal, in that piezoelectric material. That means I'm mechanically vibrating that piezoelectric material. So what happens is that analytically a voltage is being formed because of that vibration, the exact reverse of what we have seen with the inverse piezoelectric effect. Okay, here you can see that on giving an external force, that means mechanically when we are somehow we manage to mechanically vibrate that crystal, we could able to achieve a AC voltage across that piezoelectric material. Okay, so that is what, see, everything what I am saying will be there in the text, will be there as a text in your slide, so that it will be very easy for you to go through the slides. Okay, and I will move on. So this is the property of the crystals, that means the piezoelectric material that we are going to use. The piezoelectric material, it has three types. Some naturally occurring crystals are, one is Rowley salt, Rockley salt, they call this Rowley salt, and it has a property like it will have a high level of piezoelectric activity, because even if I am giving a small force, it will start vibrating very very fast. But the problem is it is very weak. Okay, it is very brittle, it can be easily broken. Okay, when we are vibrating too much, it will be easily broken. Okay, and finally, and secondly, we have another naturally occurring material, that is the tourmaline. Tourmaline is exact opposite to Rowley salt. Okay, so what happens is the piezoelectric activity is low, but it is very strong. Okay, so I have to very very hardly push at it, and it is also mechanically strong. So mechanically strong is one good thing with the tourmaline, and the Rockley salt we have high piezoelectric activity. So combining these two advantages, we have one crystal, that is quartz crystal. Quartz crystal you must have heard about previously. Okay, I'm sure quartz is not a new word to you, but anyway, it compromises of both high piezoelectric activity, and mechanically also it is very very strong. Okay, so it is not easily breakable, and also it is abundant in nature. That means it is easily available in nature. So we are the candidate quartz is selected for the crystal oscillator. Okay, and I'm taking the quartz crystal. See, this is the crystal oscillator. This is one type of crystal oscillator we can see, where either in a system, or when you open a CRO, it will be there, it might be there. Okay, definitely it will be there in the motherboard or something. Many electronic appliances will have this crystal oscillator, and the value 12 here is actually known as the 12 megahertz. It will oscillate at 12 megahertz. Okay, the equivalent circuit of this crystal oscillator, quartz crystal particularly, it is given here. Here you can see the quartz crystal is given here. The thing I am shading, that is actually the quartz crystal, and you can see the metallized electrodes are in the top and the bottom to provide the electrical contact with that with the whatever applications we are having. Okay, now this is the equivalent circuit. Here you can see RLC combination is there, series RLC combination is there. Okay, and each and every component has its own definition, and there is a parallel capacitance is also there. Okay, this parallel capacitance is due to the electrolytes, metallized electrodes that has been connected here. Okay, that's why we have this capacitance here. Okay, I'll erase that. Yes, who is that? Pranav, are you listening? Okay. Now you can see here the equivalent circuit model will have this RLC combination, and every resistor, capacitor, and inductor will have the own definition. Okay, first we will discuss about first we will say what is this series capacitance. This is CS means, S means the series capacitance, P means the parallel capacitance. Okay, this CS represents the motional capacitance, and it depends on the material's nature, that is various factors like elasticity, area of the plates that we are using, and also the thickness of the quartz material that we are using. Okay, so that based on that, this value of the CS is decided, and LS is in the same way, it is known as a motional inductance. It represents the motional inductance. As you know, why I am using the word motional, because it is the particular crystal is given a motion so that it will start moving, then only you will be getting oscillations. Okay, so it represents the motional inductance, and it depends on the mechanical mass of the quartz. Okay, generally this will be from few henries to millihenries. Okay, this LS will be from few millihenries to millihenries. Okay, and RS is obviously there will be some resistive, so some resistive effect will be there. Okay, so because of that we are representing that with the resistance RS, and usually it will be in some ohms to kilo ohms. It will be in terms of ohms to kilo ohms. As we know, as I said earlier, the CP here, the CP here, you can see, because of the CP, this CP is because of the metallized electrodes that is being given here, and that will also have some value. Okay, now we will see how this characteristic of this crystal can be analyzed. Okay, so in the place of see, take a Colpitts oscillator. So in the Colpitts oscillator we have two capacitors and one inductor. So in the place of inductor we can directly use the XL there, I mean the crystal there. Okay, the crystal can be either used as a capacitive element or an inductive element. Okay, it is based on the usage of your frequency. That means in what frequency the crystal is being oscillated. Okay, here you can see, if the crystal is oscillating at a frequency of f1 is nothing but the series frequency. F1 represents the series frequency, and F2 represents the anti-resonance frequency or the parallel resonance frequency. Okay, in the timeline here I'm just indicated this response is being divided into three parts. Okay, the middle one is inductive. So if I am going below this frequency f1, if I am going below this frequency f1, and if I am going above this frequency f2, then it will be capacitive. If I am staying within the frequency of operation is staying within the frequency f1 and f2, then it will be inductive. Okay, then your circuit will behave as inductive. This curve is actually impedance versus your crystal impedance versus the frequency. In the x-axis you have the frequency, and in the y-axis you have the impedance. Okay, so we have the series resonance. This series resonance is actually given by this series resonance here is actually given by 1 by 2 pi root of LS into CS, because series resonance, it means it depends on the series elements only, series elements of L and C combination. So LS into CS, we have within the square root, we have LS into CS, series resistance and series inductance, series capacitance and series inductance, and the parallel resonance at the frequency f2, we have the resonance frequency as parallel resonance frequency as root of LS, that is a series inductance, into CEQ, equivalent capacitance. CEQ means it will treat both the capacitance, that is a parallel capacitance and the parallel capacitance CP and the series capacitance CS. That is, it assumes like both the capacitance are are connected in the parallel. That's why we have the C equivalent as CPCS divided by CP plus CS. Okay, fine. Now, okay, we are going from one frequency to another frequency. Okay, but when we want to go for some more frequency, my frequency of operation is more than this F2. Okay, so what can I do there? So we can say that frequency is inversely proportional to the thickness of the crystal. Okay, if the thickness is very low, the frequency of operation is very high. Okay, so I can't go beyond some thickness. Fine. So, but my frequency of operation is more than that, more than the thickness that could be achieved, because more the thickness is getting slighter, my crystal may tend to broke out. Okay, at that time, crystal generally have a fundamental frequency. We are not sticking on to that fundamental frequency, but we go for the overtone frequency instead of that. Okay, overtone is nothing but the harmonics of that frequency. Okay, hope you are little aware of that harmonics, definitely, because harmonic is the additional frequency terms. Say if I'm squaring some frequency, then you will be having a plus b the whole square will be a square plus b square plus 2ab. This 2ab is actually a kind of harmonics. Okay, so we are considering the odd harmonics to generate a higher frequency. That odd harmonics is known as the overtone. Okay, so when my frequency of operation is higher, I am not sticking on to the frequency, default frequency, that is the fundamental frequency of the crystal, but I am going for a overtone of that fundamental frequency. That means harmonics of that fundamental frequency, that is known as the overtone. Okay, right. Okay, now we know that there are two different frequencies here. Okay, one is series resonance frequency, another one is parallel resonance frequency. Okay, first I am going to use the crystal at a series resonance frequency. At a series resonance. Okay, this is a crystal that has been operated at a serial resonance frequency, and you can see the value of the you can see the value of the impedance here. This is nothing but the magnitude of the impedance. Z is the impedance. You can see the impedance here is very low. The impedance at this point F1 is very low, so that's why I'm using it as a series resonant frequency. I'm using it in a series fashion. Because in the next slide, if I'm taking that circuit, the output is connected in series with that external. That means external means nothing but the crystal. Okay, I'm sure it will be very much visible here, and this in turn is connected to the feedback network. That means it is connected in the series. That means a less impedance is offered by this crystal, so a large amount of output will be appearing in the input. Okay, that is the case of series resonant mode. Okay, see, this is nothing but your LC circuit. Okay, here this combinedly it will form a kind of a tank circuit there. Okay, fine. I'm moving on to the parallel resonant mode. Okay, in the parallel resonant mode, if you just check this circuit, this is nothing oscillator. The only thing is, in the place of inductor, we are connecting the crystal there. Okay, because this crystal is having the inductive behavior. Inductor behavior is also there with the crystal, and particularly at the frequency F2, if you just check, particularly at the frequency F2, it is inductive. It is inductive in nature. That's why we are replacing the inductor in the place of replacing the crystal in the place of the inductor of the Colpitts oscillator. This is nothing but a Colpitts oscillator. What we just discussed. The only difference is we have a RFC here. RFC means radio frequency choke here. Anyway, RFC or resistor, whichever you like, you can draw there, because ultimately the operations are same. Okay, fine. So for having a largest impedance value there, we are connecting that crystal in the parallel mode. Okay, now some crystal parameters. Finally, we are considering some crystal parameters that has to be looked while I'm selecting a crystal. Firstly, we have to know what is the frequency of the crystal. Okay, that is obviously that has been written on the top of that crystal, whatever we are selecting. And we also want to see what is the drift in the crystal frequency over time. Okay, drift in the frequency means if my crystal is oscillating at 10 kilohertz, assume my crystal is operating at 10 kilohertz. At some time, over the time, it may start operating at 10.1 kilohertz or 10.2 kilohertz. Very minor drift in the frequency. Okay, so that drift should not affect your operation when you are using that crystal with the circuit you are designing. That should not be that frequency, small change in drift in the frequency should not, make sure that small change in the drift in the frequency should not disturb your circuit. Okay, and the third one is the mode of operation. Either we are going for the fundamental mode or the overtone mode. Overtone mode in the sense, fundamental mode in the sense, we are sticking on to the basic basic frequency that has been generated by the crystal, or we are going to use the harmonic version of it. Okay, and finally the thermal stability, temperature stability, obviously, and also we are worried about the power dissipation level. This power dissipation level is as low as possible. Okay, because we don't want our power to be get dissipated unnecessarily. Okay, so these are all some crystal parameters that we have to look for before developing a crystal for our oscillator or some other circuit. Okay, fine. Okay, with this I'm ending the session. Okay, so I'll send you this material now. Please give your honors. Be here for 2 or 3 more minutes. You let me know if you have some doubt.